Good morning to one and all. This is Dr. YVNR Swami, working as an associate professor in the Department of ECE. Today, I am going to teach one topic, that is Gauss law, its limitations and applications in the subject of electromagnetic waves and transmission lines. Gauss law. Its statement is a very simple one. Now we'll see its statement, its proof, its limitations and applications. So if we know electric field intensity due to point charge, line charge, surface charge, volume charge, then automatically those becomes the applications in Gauss law. Okay. And we have to find electric field intensity as well as electric flux density in Gauss law. Okay, so coming to the statement of Gauss law, psi is equal to Q enclosed. Psi equal to Q enclosed means Gauss law states that the total electric flux psi passing through any closed surface is equal to the total charge enclosed by that surface. Total charge enclosed by that surface. It is a Gauss law. Gauss law states that the total electric flux psi passing through any closed surface is equal to the total charge enclosed by that surface. Okay, that is psi equal to Q enclosed. So here we are going to prove the del dot D equal to rho V. Del dot D equal to rho V. Del dot D means divergence of electric flux density is equal to the volume charge density. So that is the Gauss law statement. Now we are going to prove this one. And this del dot D equal to rho V is the one of the Maxwell's equation in electrostatic field. So now we are going to prove this one. Okay. So first of all, already we know that from electric flux density, D is equal to d psi by ds to an. D, electric flux density, D equal to d psi by ds into an, where an is the unit normal vector. And from this formula, we will know that d psi is equal to d dot ds. Then what happens psi? Psi is equal to surface integral of d dot ds. Okay. So from the electric flux density, d equal to d psi by ds an, where an is the unit normal vector. From this one, d psi equal to d dot ds. Therefore, psi is equal to surface integral of d dot ds. So, how d equal to d psi by ds into an becomes d psi is equal to d dot ds. So now I will explain here once. All of you look at this one. So now this is the point charge plus Q and it is the point charge minus Q. Now flux lines are originated from the positive point charge and terminated at the negative charge minus Q. then flux lines are originating in this direction, So now we are taking a small differential area ds, and its direction is in this direction, an. So now we know that d equal to d psi by ds, and here d is the electric flux density that is normal to the surface. Electric flux density is normal to the surface, and ds is the differential surface area direction. Differential surface ds is the differential surface area. Its direction is also normal to the surface. It means ele- electric flux density d direction in this direction, and differential surface area direction also in this way. Means d and ds directions are parallel. Then these two are parallel, then the angle between these two are zero. Okay, hence d psi means d dot ds means, already we know that dot product a dot b equal to ab cos theta. In the same way, d dot ds equal to d ds cos theta. Here the angle between d and ds is 0. Then theta equal to 0. Cos 0 is 1. Okay. Therefore, angle is 0. Then d dot ds becomes a dds. In this way, d psi equal to dds. Therefore, psi equal to surface integral of d dot ds. D dot ds becomes a dds. Okay. Hence, d psi equal to dds equal to d dot ds. So, from this analysis, we are writing uh, d psi equal to d dot ds from the equation d equal to d psi by ds into an. So that is the happen thing. Okay. So finally, we will get psi is equal to surface integral of d dot ds. Surface integral of d dot ds. Now we have to apply the divergence theorem. What is the divergence theorem? The relation between the surface and volume integrals is called as divergence theorem. So now apply the divergence theorem to this equation. Then what happened? Psi is equal to surface integral of d dot ds, that is equal to volume integral of del dot d of dv. Volume integral of del dot dv. Okay. So now the what we get finally, surface integral psi is equal to surface integral of d dot ds is equal to volume integral of del dot d of dv. So this is the obtained equation from the electric flux density. Okay, from this electric flux density. Okay, so now we know that the total charge enclosed by that volume is Q is equal to volume integral of rho v dv. We know that the total charge enclosed by the volume is Q equal to volume integral of rho v dv. So now, according to the statement of Gauss law. What is the statement of Gauss law? Statement: the total electric flux psi passing through any closed surface. The total electric flux psi passing through any closed surface is equal to total charge enclosed by that surface. Now we have the flux psi is this one, and we have the charge this one. Now we are equating these two. Psi equal to q. Then what is the psi? Surface integral of d dot ds is equal to volume integral of del dot d of dv. Then what is the q? Q equal to volume integral of rho v dv. Okay. So now we are we are equating volume integral of del dot d of dv equal to volume integral of rho v dv. So this one is called as integral form of Gauss law. Integral form of Gauss law. Volume integral of del dot dv, del dot d of dv equal to volume integral of rho v dv. This is called as integral form of Gauss law. Gauss law. Okay. Then just removing the volume integrals on both sides. Volume integrals on both sides. Then what happened? Here it's just del dot d equal to rho v. Del dot d equal to rho v. This is the differential form of Gauss law or point form of Gauss law. Gauss law. Okay. In this way, we are proving del dot d equal to rho v. That is divergence of electric flux density is equal to the volume charge density. Volume charge density. Okay. So this is the differential form or point form of Gauss law. Gauss law. Okay. So now coming to the limitation. Limitation. This above equation states that volume charge density is same as the divergence of electric flux density. So statement of this one is divergence of electric flux density is equal to the volume charge density. Okay. Now coming to the limitation, the Gauss law is used only for symmetric charge distribution. Gauss law is used only for symmetric charge distribution. This is the limitation of Gauss law. So it is only applicable for symmetric charge distribution. So for non-symmetric charge distribution, it is not used. So this is the limitation of Gauss law. Limitation of Gauss law. So then coming to the applications. This Gauss law is used to calculate the electric field intensity, electric flux density. Gauss law is used to calculate electric field intensity as well as electric flux density, because there will be the relationship between electric field intensity and electric flux density. D is equal to epsilon into E. Epsilon into E, where epsilon is the permittivity. Epsilon is equal to epsilon naught into epsilon R, where epsilon naught is the permittivity in a free space. Okay, and epsilon R is the relative permittivity. Relative permittivity. So, permittivity in a free space value epsilon naught is equal to 8.854 into 10 power minus 12 farads per meter. Okay, epsilon R relative permittivity value will be varying based on the medium. Okay, so now applications of Gauss law are applications of Gauss law are infinite line charge, infinite sheet charge, uniformly charged spheres, and point charge. These are the four applications. So point charge. Charge, a small charge occupies very small area. A charge occupies very small area is called as point charge. The charge is uniformly distributed along the line is called as line charge. The charge is uniformly distributed over a sheet or surface is called as surface charge. And the charge is uniformly distributed throughout the volume is called as volume charge. So what we find it in the electric field intensity, that is in continuous charge distribution, electric field intensity due to continuous charge distribution. So point charge, line charge, surface charge, volume charge. In the same fashion, here also we are going to find the electric field intensity, and based on the relation between electric field intensity and electric flux density, we are going to find the electric flux density also. So finally, the applications of Gauss law are point charge, line charge, infinite sheet charge, and uniformly charged spheres. Uniformly charged spheres. Okay. So once again, I am revising these things. These things. Statement of Gauss law. Statement of Gauss law. So Gauss law states that the total electric flux psi passing through any closed surface is equal to the total charge enclosed by the surface. That is, psi is equal to q enclosed. From this one, we are going to prove the del dot D equal to rho V. That is, divergence of electric flux density is equal to the volume charge density. Volume charge density. Okay. And then limitation of Gauss law is it is used only for symmetric charge distributions. Symmetric charge distributions. And applications of Gauss law are point charge, infinite line charge, infinite sheet charge, and uniformly charged spheres. Uniformly charged spheres. Okay. I hope this topic is clear to all the viewers. Thank you. Thank you, one and all.